Welcome to the review session for the final exam in ECE 442-542. And I said I might cover this material more in the review session. I think I'll cover it less. I think you know what's going on. It's going to be a comprehensive final. It's uniformly distributed across the entire semester, and I'm thinking there will be 15 questions. And those 15 questions will be equally weighted, meaning problem 1 will be worth 10 points. Problem 7 will be worth 10 points. Problem 15 will be worth 10 points. You'll have 2 hours from 6 a.m. from 6 p.m. to 8 p.m. on Friday to complete your final. Yes. And those problems probably will, the question was, will each of those problems have multiple parts? Only up to 6 levels of parts for each problem. But they'll probably be shorter answer than the hour or the 75-minute exam problems. They may have multiple steps, but it may just be one problem, meaning there may not be a part A and a part B and a part C. But there may be multiple steps to get you the final answer. And some problems may be much more involved than others. And that doesn't mean that you're missing something or that you're not doing something correct. Some might just be easier for you than others. And some might be more involved just by design than others. Some might be very quick to work. So they may not be uniformly difficult, even though they're hopefully uniformly distributed across the material. Is that clear? You have 4 pages of notes. You have the transform tables. You can bring a protractor, etc. And then the last 4 are no's. No books, no notebooks full of notes, no cell phone, and no computer. And I haven't decided. I might actually assign seats for the final. So you might want to get here a few minutes early. Maybe I'll put you in different locations. I haven't decided. All right. Now, in terms of the class, one piece, a big piece, is modeling. And by modeling, I'm meaning you need to be able to model these systems in many different ways and move back and forth between those ways. You need to be able to work with difference equations and maybe put that into an all delay block diagram. Or maybe you want to go the other way. From an all delay block diagram, can you move into a difference equation? And you may not want to do that directly. Maybe you'll get a transfer function and then do the cross multiplying and then get your difference equation, but you should be able to go back and forth between a block diagram and a difference equation. Once you have a difference equation, you should be able to take that into the transform domain, meaning now you should be able to z-transform that difference equation, or if you go the other way and inverse z-transform to get the difference equation. You should be able to go back and forth that way. And once you have an all delay block diagram, you should be able to obtain the state space representation. And do you remember how you do that? You need your states to be the outputs of your delay blocks. And is the state space representation unique? No. We might have 50 different state space representations for the same system. And you should be able to go the other way. If I give you a state space representation, I hope you can draw the block diagram for that. Now you just need to put together a bunch of delays. How many delays will you need? Depends on how big your state vector is, doesn't it? So you have to know how many state vector components you have, and then you'll know how many delay blocks to introduce. And that could be kind of a messy looking diagram, but that's doable. And you should be able to go, maybe not directly back and forth, but if you have a state space representation, you should be able to Z-transform that. We did that just in the last lecture to obtain G of Z for a state space representation. And if you have a transfer function, actually, once you know these canonical forms, you could, by inspection, create a state space representation. But if you didn't know that, you could sort of go the other way around in your block diagram. You could go up, get a difference equation, put that into an all delay block diagram, and then label the outputs of your delay blocks and get a state space representation. So you can chase your tail around, or you better be able to, in this collection of models. The other thing that I might give you is sort of the next topic that we talked about was how do you solve difference equations, or how do you solve dynamic behavior problems, so that if you're given any of these models, and maybe an input waveform and an input waveform, you better be able to compute either the transform, the Z transform of the output, and the time domain sequence Y of n, or just Y of n. And if you have Y of n, maybe I'll ask you different things. Maybe I'll simply ask you for the structure of Y of n. Maybe I will ask you for the complete solution. You need to be able to do any or all of those problems. Meaning I might give you an all delay block diagram and give you a signal, a waveform, and say, give me the output, the closed form expression for Y of n. It may not start as a difference equation. Maybe I give you a state space and you go, wait a minute, I've never done this. Come on. Once you have a state space, you can go to any of those other blocks and solve whatever you need to get the answer that you're looking for. Is that clear? Now, that being said, we can also just talk directly about Z transforms, and there I could ask you to Z transform signals or waveforms or systems. And you need to be able to go the other way. Inverse Z transform signals and systems. And if you're going on an inverse problem, What's some other piece of information you might be interested in or need to pay attention to? The region of convergence. So you need to understand the region of convergence, and in particular, again, you might be looking just for the structure. You might need to know where the index is valid. Is it one-sided? Is it two-sided? Is it a positive indexed sequence? Is it a negative indexed sequence? You need to remember what that means and how that's related to your region of convergence. And all of that, if you sort of forget, you can just write down the definition of the Z transform and say, what is there a point in the Z plane that's in the region of convergence, and does that tell me something about which of these coefficients are zero or non-zero? And that might tell you which side, right-sided, left-sided, or two-sided. In general, if you have a region of convergence that's beyond all of your poles and goes off to infinity, what's the time index range that you're talking about? Now Z equal to infinity belongs to your region of convergence. And if you remember, and if you don't remember, go back and look at the Z transform definition, and that's going to basically say I cannot have negative indexed time domain signals if that point is in my region of convergence. So that corresponds to causal sequences, positive time indexed ends, because there you have Z to the -1, Z to the -2 being weighted. If you have an annular region of convergence, and your region of convergence cannot be disconnected, can it? You have to have a connected region of convergence. It's either an inner circle, a donut, or an outer region. It can't be an inner circle and an outer region for your region of convergence. It can't be disconnected. If it's annular, what kind of indices are we looking at? It's two-sided. And then the other one that we didn't talk about is the opposite. If your region of convergence is interior to all of your poles, then it's a negative index sequence. Is that clear? Another topic is discrete equivalents, and you can sort of think of this in falling into two classes. This is all the same class, but two different strategies for doing discrete equivalents. The first one is if you have a physical plant. And maybe that's modeled with a transfer function in the S domain, a G of S, or maybe it's an x dot of t is equal to a x of t plus b u of t, y of t is equal to h x of t. You now have a continuous time plant, and you're actually wanting to control that digitally. Then you can't just apply a sequence of numbers to this analog system. It won't behave properly. You need to convert that sequence with some hold network or device that will, in a zero-order hold, it's just going to hold constant whatever it was that you supplied at the input. At the input to the zero-order hold, if you gave it a 1.7, it's going to hold that for one sample period. Then maybe you change it to 1.9, and then it holds 1.9. You have a hold so that now going into this plant is a continuous time waveform. If this is what you have that you are trying to find a discrete equivalent for, then this is what you use the zero order hold equivalent, which is going to produce a G of Z. What's that look like? That's this 1 minus Z inverse, Z transform of G of S over S. Or, if you were given a state space, then you find this phi and gamma in terms of your system matrix and your input matrix in the state space continuous time representation. And you need to know how to compute all of those. Is that clear? That's one piece of the discrete equivalence, is if you have a plant and you go, well, what discrete equivalent do I use? Well, you can say, I'm going to use a zero order hold equivalent, or maybe the question might say, find the zero order hold equivalent of this plant G of S. Then you know that you need to find that G of Z. Maybe I give you a G of S and I ask you to find the state space zero order hold equivalent. And you could do that several ways, but one way would maybe to find the G of Z and then get a state space representation. You go up to the very first set of topics and you work your way around that square to find the state space from a transfer function. Is that clear? That's one set or kind of or type of discrete equivalent. The other is when it's not so much a plant that you're wanting to move from the continuous time into a discrete time equivalent. Here, maybe you have a, what did we call controllers? C's or D's? C's. My notes say D. I never obviously remember. You might have a controller that somebody has already designed from a 441 class. Or maybe they've had a 441 type class and they give you a C of S. Or maybe that's a filter, an analog filter that they've designed, maybe on a 320. They now have designed a fourth order low-pass Butterworth filter and they have it in the form of a transfer function. And they say, I don't want to do this with parts from the stock room. I don't want to build this on a circuit. I want to build it in my tablet. I want my computer to do this signal processing. I want to do a discrete version of this. Now you don't do a zero order hold equivalent because now you really have a signal coming in and a signal coming out. You're not really trying to control anything directly. You just want to preserve the behavior of this C of S with your discrete implementation. Here is where you would do either the numerical integration or the pole zero mapping approach with the discrete equivalence. Meaning now you're trying to find a C of Z either via numerical integration or with pole zero mapping. Now in both of these approaches or types, I haven't yet talked about the sampling or the sample period, have I? If you're doing a zero order hold equivalent of a plant, how do you find T? Or how do you need to find T? Or will it matter what T is, the sample period? How do you find the sample period? This is a problem you'll have to solve when you get out. You'll have to come up with a T, and you won't want to tell your boss when they go, how'd you find your sample period? I don't know, I just picked one. Who is your digital control instructor? Where did you go to school? I don't know. Somebody wrote me a letter of recommendation. I don't want to admit who it was. Okay, now how do you find T? Pardon? You can find the natural frequency, but if you know that this is maybe going to be in a control environment, you probably want to sample fast enough to where your closed loop dynamics are not negatively impacted by this slow sample period. So your capital T, or your sample period, usually here is foreshadowing what you're going to do with this model. It's usually based on your closed loop dynamics or the settling time in the closed loop system, right? So here in this zero order hold equivalent, the T, let's say, is based on closed loop dynamics. Now, if you're not really going to close the loop, then it really just will depend on your natural frequency or your highest frequency in your system, right? So there's a lot of give and take here. That's why you've taken the class, so that you understand when and why you pick the T that you pick. You don't just say, I don't know, I just picked one. Picked one? Where did it come from? What did you base that on? Versus down here, now what does T depend on? Here it may depend on the signals that you're filtering. You may be low-pass filtering a bunch of noisy or high-frequency content signals. So T may have a different reason for its value here versus in the zero-order hold equivalent. If it's a controller, then it's probably based on your closed-loop dynamics again. So what you use for T is going to be important, and there's some justification behind it. Is that clear? And I might ask you to find the T, or I might have you say, oh, the T is based on so many samples in a settling time, or so many samples in the frequency of oscillation, the damped frequency, or in the peak time, something to that effect. You may need to figure out what the settling or the sample period is. In you doing the pole zero mapping, what are you remembering? What's the relationship, or what's the equation? And I could say you may want to be clean when you're doing this. Zest, right? So, see, it worked. Z is equal to E to the ST, zest. So that's your relationship for doing the pole zero mapping. What's the other sort of important idea or concept that you have to play with pole zero mapping? Pole zero excess or infinite zeros. Usually we map those where? Z plus 1 factors, right? Is that true? When you put those in the numerator, those are values of Z. When Z is equal to -1, that causes that to go to 0. Those are infinite, or points at infinity in the Z plane, or can be viewed that way. If we're doing numerical integration, what are the options there? We have 3, don't we? Or we talked about three, a forward, a backward, and a tuscan, or trapezoidal, which is really sort of a linear combination of the first two. In the forward, we were replacing S with Z minus 1 over T. In the backward, we were replacing S's again with a Z minus, whoops. Again, a Z minus 1 over T, but now we have a Z in the denominator. So these look very similar in terms of these transformations. And the tuscan is really just sort of an average of the two. We're replacing S, again with a Z minus 1 over T, but now we have a Z plus 1 over 2. And you might see this written as a 2 over T with those two ratios. But it's very similar. I mean, it's has similar structure to the forward and the backward. And which of these preserves stability? The bottom two, don't they? The backward and the tuscan, or the backward and the trapezoid. Those preserve stability between the S-plane and the Z-plane. Questions on that? Desired regions. Now that we know how to model and transform things between S and Z, we need to be able to go back and forth in this context between maybe performance specifications to Z-plane pole locations, or from Z-plane pole locations to performance specs. Think back on maybe exam 3, problem number 4. Didn't I sort of ask you to go the opposite way? Make sure you can go back and forth. If I give you percent overshoot, what are you thinking? Zeta, aren't you? If I give you settling time, what are you thinking? Disks, aren't you? So the zeta is your heart shapes, your logarithmic spirals, your settling time. Now you're trying to get into smaller and smaller disks if your settling time is getting less. And then you have your peak time. That's now this angle, isn't it? Or time to peak is pi over omega sub d, but omega sub d is related to theta sub d, so that now we could actually say omega sub d is theta sub d over t, so that this is now, in terms of an angle, if you make your angle bigger, theta sub d angle in the z-plane, you're shrinking your peak time. Is that clear? Or you might have found a transfer function that you now identified as the closed loop transfer function, and now you're asked, what's the settling time? What's the peak time? What's the percent overshoot if this was an ideal second order system? So think back about those different conditions. If you now have, for example, wow, I don't know if this is equal in terms of direction, so my angles might not be correct, but if somebody gave you an R and a theta, you could pin that point on that grid and immediately eyeball what you have in terms of angle and zeta. If somebody said, oh, your closed loop poles are at, let's say, 0.6 plus J 5. Why did I pick that? I don't know. So now you're about right there for your pole. But now you have a pretty good feel for what your zeta value is, right? It's one of those logarithmic spirals, and you can just eyeball it if you wanted to kind of get a good fuzzy feel for what you're going to calculate or numerically determine. And then from zeta, what do you know? As far as now percent overshoot, if this was behaving like a pure two-pole system, what's your percent overshoot? Now that you have a zeta value of, let's say, 0.38, you could plug that in, and now you know what your percent overshoot is based on a real value for your pole and an imaginary value. You have those in rectangular form, or maybe somebody gives you the radius and the angle. You could plot that also on this diagram and start to interpret. Here, if they gave you that star and they said, oh, what's the peak time? Now you can find your theta sub d. Your theta sub d, I think this is supposed to be divided into 10 wedges on that half circle, so that each of these little wedges is 18 degrees. Now we're a little bit beyond 36 degrees. Or what? 2 pi over 10 in terms of radians. Is that okay? And you can then compute what your peak time needs to be. Your peak time now is pi over omega sub d, but we remember theta sub d is omega sub dt, so that if you solve that, you now have that. And once you have theta sub d in radians, since pi is in radians, now you know how many sample periods you have in your peak time, just by sketching that triangle. Is that clear? Or if you know the radius, now you've measured the radius, and you see how far away you are from the origin, then what do you know? Well, now you know r n sub s is equal to 0.1 for your 1% settling time, and if you know r, you can solve for n sub s with a little logarithm. And now you know how many samples it's going to take you to settle to your 1% settling time. Is that clear? All of that by just plotting a point on that grid. And that might come from finding the closed loop transfer function. Maybe somebody gives you the controller and they give you the plant, and you put it all together in a closed loop system, compute the denominator, which gives you your closed loop dynamics, and you have one of your complex poles living right there. Maybe you had 6 different complex poles. How do you decide which ones you use? I don't know if I should color that up anymore. So let's go back here. And now let's, helps if I get on the right. What if somebody now says, oh, you know what? You have poles there. That's your, and let's say those are closed loop poles. What have we agreed to in this class that you can use to determine the behavior, the generic sort of the general feel behavior for this system governed by these 5 closed loop poles? We pick the dominant poles, don't we? I hope he doesn't. I hope he gives me full credit for that. define dominant, right? That's what I would ask. I would say, you didn't tell me what dominant means. What's dominant mean? The ones that are moving the slowest, right? I'm assuming now these are all inside the unit circle. So we're stable. So they can actually dominate. Which of these poles would you use, or pole would you use to determine what we've agreed to be determining the settling time, peak time, and percent overshoot? Although it's not what's going to really happen because they all sing together. You now have a choir of 5 poles. Some are a little lower than the others, but we're concentrating on the lower ones here, aren't we? The dominant ones. Where's the dominant? Pardon? On the real? So all of these actually have a real component, don't they? But this one is easier to find in terms of its settling time because I can measure that pretty easily, and I have an e to the, or I have a z, that value raised to the n. But that one's going to collapse quite quickly, isn't it? Because it's not very far from the origin. That's going to be a fast one. So now you're looking at, really, you're sort of looking at this bullseye pattern. And now what you want is you want to say, okay, if all of those are inside the unit circle, the ones that are dominating are the ones that are closest to the unit circle. That's what we've agreed to. Yes? So even if you had so the comment was, even if you had a pole that's outside the unit circle, yes, it's going to dominate because it's going to make your plant stink, burn up, isn't it? It's going to dominate everything. Your lab partner's going to go, what are you doing? You're dominating this whole lab. Well, I wanted to prove what I could do. I wanted to make a point. Ooh, that was the wrong point to make, huh? But yes, you're correct, but that's probably not what you want because that's not going to dominate for long. It's going to burn everything up, and then you're going to have to go to the stockroom and get some more parts. And maybe next semester we'll charge you for those parts, especially if you've had a course that you've learned that that's the wrong design, right? So in this case, we would use these poles. That's what we've agreed to, but I hope you realize that all of those are singing together and they will influence everybody else, and especially if they're clustered quite closely together. They're really going to sing together and influence each other. But for this class to get something to grab a hold of and give some numbers to, we're going to just say, let's play with those that are closest to the unit circle. Questions on that? Yes? So now the question was, can we have, I'm going to rephrase it, can I have that by itself? Is that the question? So now will you see that, or can you see that? And this answer has 2 parts, or 2 answers. You could if you allow complex coefficients in your equations. If you had a transfer function and you allowed complex coefficients, then you could have a single complex pole. But we usually have real coefficients in our transfer functions, don't we? So those real coefficients are forcing, anytime you have a complex pole, you have its conjugate. And that's going to then lead to having real coefficients in the numerator and the denominator. So if you allowed for complex coefficients in the denominator, you could have just one isolated complex pole. But we play with things that are nice. We are just saying, in reality, we have real coefficients. We have real things happening. We get into complex when we start worrying about making our analysis easier, and so we allow for complex numbers. But we are going to say we have real coefficients, so we won't have that situation that you ask. But that's a valid question. Other questions? Yes? So you might have a situation, but I'm not sure it's going to be real. We'd need to talk about that maybe offline. But here, what I'm suggesting is what we'll be playing with in this class will have real coefficients, and those real coefficients in the denominator will lead to complex conjugate pole pairs. So we won't just have that one isolated pole. We're not going to allow for constraints. I'm not quite sure I'm seeing what you're asking, so we could talk about that later. Questions? Other questions or comments? Now what do we do? Now we get into design. And I think the first one that we started playing with was maybe the one that was more difficult to pronounce. Design via Ragazzini. And there we did have constraints, didn't we? Anytime we start playing with Ragazzini, we had constraints or restrictions. For example, if I give you, do I have some that what if I give you a plant G1 of Z that is equal to 4Z over Z minus 1/2 Z minus 3/4? Do we have any Ragazzini restrictions for this plant? Do you remember? If you don't, you need to make sure you start remembering for the final. We had 4 constraints or restrictions when we had Ragazzini. Are any of those in play for this plant? So now I guess you just have a yes, no, huh? Flip a coin. How many are saying yes? What? I didn't say anything about steady state accuracy, did I? And we probably won't deal with that because that takes a little bit more computation or processing to worry about on the exam. But this one does have one, doesn't it? It has the first one, which is the pole zero excess. This one says restriction 1 is sort of in play, which says that T sub C of Z needs to have a pole zero excess of at least 1, right? And that's really all you have to worry about here. And somebody might say, I need closed loop poles at certain locations. Well, you can make that in your T sub C of Z. But then you would need to have a pole zero excess of 1 or more. What about if I gave you another plant? G sub 2 of Z is 2, Z minus 2 over Z, Z minus 1. Any constraints or restrictions? Which ones? What? 0. I didn't think we had 0 restriction. 1, 2, 3, 4. And it's really not critical that you memorize the 1, 2, 3, 4. You just have to know how to apply that you have 4, right? So if you're in C, 0, 1, 2, 3. Is that right? So yes, it could be 0. Is that the one, the pole 0 excess one? Maybe because it deals with zeros, you like to call it 0. So restriction 0, I'm calling it restriction 1. The pole 0 excess needs to be 1, right? What else? So restriction 2, I think, is what we called it, wasn't it? We have to, what do we do with the unstable 0? We need to make sure and force it to be in our T sub C of Z, don't we? We can't cancel it, so now restriction 2 says that this Z minus 2 is a 0 factor in T sub C of Z. Is that clear? Anything else? We do have restriction 3, don't we? Because we have an unstable pole. So now we need the quantity 1 minus T sub C of Z evaluated at Z equal to 1. We want that to be equal to 0. We need that numerator, we need that expression to have a 0 at Z equal 1. So we find the 0, or the numerator expression of that 1 minus T sub C, and we set that equal to 0 when Z is equal to 1 and solve for whatever unknown variables we have in that expression. Is that okay? Is that enough for Ragazzini? Then we moved on to PID. And I think there we started learning about root locus, didn't we? But before we get into root locus, what's the benefit of I? And you know when you finish this class that you're not going to say this is a PID, is that right? Yeah, we talked about PIDs. Who was your instructor? I don't know. PID, proportional integral. What's the benefit of I? Steady state accuracy, right? What's the D, the derivative? What does that give you? That maybe helps you with your transient. That may speed up your response. Now, if we're dealing with PID controllers, we probably need to understand root locus construction. And not only construction, but also how do you use root locus in a design setting. But in terms of construction, suppose I give you the following. Suppose I give you, where do I want to start here? Suppose I say here is a G of Z that is Z minus 1/4 squared plus 1/4 squared over Z times Z plus 1/2 squared plus 1/2 squared. And I said, sketch the root locus of that. Do you see the pattern to begin with? If we say root locus, now you're playing the game, aren't you? X's and O's. Do you have any O's? Where are they? Everybody get that? Did you pick that up? It's getting late. Where are my zeros? I guess I have them. I think that's what I overheard. Well, no one wants to commit. Are they on the right half side or the left half side of the z-plane, the zeros? They're in the right half plane, aren't they? Which isn't a bad thing in the z-plane. In the s-plane, you don't want anything in the right half plane, or that's usually where you get a little nervous. But here, these are at 1/4 plus and minus j 1/4, aren't they? The way that I factored that expression. The poles are now, oh, and I need to, I guess to be consistent with what I've been doing most of the semester. The poles are here, aren't they? At minus 1/2 plus and minus j 1/2. So make sure you get the signs correct by the signs in the expression. And then we have a pole right there. What's that root locus going to look like? You have any idea? From the origin towards minus infinity. Ah, you're picking the easy answer, aren't you? Do we have any other asymptotes? You've identified one, correct? How many zeros at infinity do we have? One. So we only have that one asymptote going off to minus infinity. Now what's happening? Oh, I don't know. I don't remember how to do this. Departure angle. Who are we departing? We're leaving the poles, aren't we? And approaching the zeros. So we have departure angles from the poles and arrival angles to the zeros. What's going to happen? Well, if you find the departure angle, that's going to tell you which way you're going. Suppose you find that it's doing this. Then what happens? Does it do this? Probably not, huh? So you're going to find, you could calculate, and I may ask you to calculate the departure angle. That might be one of your problems. And I may not ask you to do anything else. Do you know how to just calculate the departure angle? You should be able to get your zero angles and get your protractor out or your calculator and compute these. But now, what's to tell you if it goes like this? This one's going here, one of those goes there, one of those goes here, and then this pops up here and does this. Would you have guessed that? Could it do that? Is that possible? How could you validate whether or not that's the case? If you find the departure angle is, let's say, 260 degrees, that's consistent with this, isn't it? Now, what's another check? And then you could say, oh, my arrival angle is 190 degrees. I'm coming in at 190 degrees, right? Well, that's consistent with this. But what's another way? Well, you could check the gain along this real line if you had some time. And you could evaluate the gain for those negative values of z, and what would you be looking for? We're cranking up the gain. Right here, as I move this way, what's the gain doing? Increasing. So that point is a relative minimum, isn't it? If this point right here is -1 and this is -1/2, if I looked at z between -1 and -1/2, well, and I just found that it was monotonically increasing from -1/2 to -1, then I don't have this kind of behavior, do I? It never has a relative minimum. But if I am going from z equal minus 1/2 with k, and I see that k is decreasing and then it increases, whoa, I have a relative minimum. I have a re-entry point there. Those two branches are coming in. One's going left, one's going right, and so what should I have here? A departure point, right? A breakaway point. Not a re-entry, but a breakaway. And that's going to occur at a relative maximum. Because as I get closer to this, my k is decreasing, isn't it? Because that's where I started, was at the pole. You could contrast that root locus with the following. You might now say, oh, here's a different root locus. Let's say that this one, oh, I'm not even going to give you the G, I'm tired of writing. Let's say that this one is now over here at 1/2 plus and minus j 1/2. We still have a pole there, but now these poles are at 1/4 plus and minus j 1/4. Now what's the root locus look like? You know that, right? You better get that. Even if I ask for departure angles or arrival angles, you could at least maybe do that and say, well, maybe he'll be nice. But you could do the departure angle, and this one actually, and I can't do the mirror image of that, but you kind of get the idea. It doesn't re-enter and depart or break away. So this, if you calculated k from 0 to minus infinity, k would just monotonically increase. It wouldn't be a decrease and then an increase. And that's how you could sort of justify or verify or validate this picture versus that picture. And these patterns all depend on the relative spacing of these poles and zeros. Do you see that these poles and zeros are sort of like these poles and zeros, but they're a little different? And you're guided by the departure angle, the arrival angles are about the same in both. The departure angles are a fair amount different, aren't they? And in this one, the way that you might verify that is say, do I have a relative minimum or a relative maximum on the negative real line? And if I don't, then I'm not re-entering or breaking away. Is that clear? How you can sort of start to check these ideas? After and with PID controllers, you better be able to sort of know where to place your zeros. And you have two of those to place. We also need to worry about general Z-plane design, don't we? Do I have any examples, or are we exampled out? Shouldn't ask that question. You'll flip the coin. What if I gave you a system, and let's say this is 1, and now you have a pole and a 0 and a pole? Can you stabilize that with a controller? Is it stable in the open loop? No, because that rightmost pole is zipping off to that 0 if we have negative unity output feedback, right? So how do we get rid of that branch between that rightmost pole and the 0? What's one strategy? We might want to add a 0 over there somewhere. Can I do this? No. That's where you'll lose 100 points on a 10-point problem. You can't, and why can't I cancel that? Well, you canceled this guy. What's the deal? You're changing the rules on me. What's critical? Stable versus unstable. We can never, 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 never cancel poles or zeros outside the unit circle, can we? Doesn't matter what they are, you can't cancel them with a pole or a zero. You could add a zero right on top of a zero, couldn't you? That's okay, but you can't cancel things. Here you might actually want to put that zero there. Can I say that's good? What's wrong with that controller? Pardon? Will it always be unstable? This one is going to be non-causal, isn't it? This one is going to have a numerator and no denominator, and this is sort of an anti-causal. We can't have just a numerator. We have to have a denominator. So we have to have a pole there. So this was kind of a trick question. If this is all we could do, if we could do this, this wouldn't be a bad thing, because now this would come here, this would go there, and as long as you don't crank up the gain too much, you'd be okay. Right? But we can't just add one zero. We can add just one pole. Now I don't know what I'm going to erase. I knew it. So we need to add another pole, don't we? That zero is not in a bad spot. But we also need to probably put in, we do need to add another pole so that we have a causal controller. Now we may have to just kind of hope for the best, because we have that eventually, we'll get there, won't we, between those zeros. These two are going to meet. This one's going to go off there, and these two are going to go here. And what do we have to hope for here? How do we sort of verify that we can or can't, if that point is 1, how do we verify whether or not we've stabilized the system? Yes. So the gain to get to 1, which is right here, we need to get this pole, this rightmost pole, inside the unit circle, don't we? And we hope that in the process of cranking up the gain k to get to that, this leftmost pole doesn't zip outside -1. So what we're hoping is that we get something like that. And this guy at the origin, he's zipping over here, isn't he? So we're going to have 3 branches. And what we hope is that maybe we crank it up a little bit beyond that, and maybe our closed loop ends up being there, there, and there. That's what we would hope to have happen. Questions on that? Yes. Yes, so you can't just add zeros. You can just add poles. You can just add poles, but you can't add uncomplemented zeros. Zeros are lonely. They need poles to feel good. Their zetas will be damaged. I told you it's getting great. Okay, are we good? We have one more topic that I better make sure you're aware of, and I'll just say we've been talking about that. You need to worry about state space design. And what you need to worry about there is full state feedback and reference input. You don't need to worry about integral control, okay? But you do need to be able to find an n sub 1, a non-zero gain on your reference input. Is that clear? So 48 hours from now, you'll be gone and happy, okay? I want that to be the steady state, the final value. Yes? So that's a good question. I have a little bit more than 24 hours to create the solutions. Hopefully they will get posted shortly after they get turned in. That's the idea. You'll have maybe not 24 hours, but you'll have some time to review the solutions to homework 8. That's the plan.